Hey there, math lovers! Welcome to this next video of our channel. This time we have found, let's say, a very beautiful problem in my opinion from Russian Math Olympiad of 1995, the regional phase, so the second phase. It seems to be a geometry problem, but the solution we will propose, it is very number theory flavored. The problem states, the lengths of the sides of a quadrilateral are natural numbers and each of them is a divisor of its perimeter. Prove that at least two of the sides of the quadrilateral are equal. Please, if you have a solution to this problem, pause the video and write it down on the comments. If not, let's go through a solution step by step together. You already know the drill, we have covered the solution in order to go through it step by step together. So, as the problem states, we are asked to prove that when the length of the sides of the quadrilateral, which we have taken here an example, ABCD, are natural numbers and each of them is a divisor of the perimeter of the quadrilateral, prove that at least two of the sides of the quadrilateral are equal. So, for the proof of this problem, we will argue by contradiction. Let's call the sides of the quadrilateral as x, y, z, and omega. Then the perimeter of this quadrilateral will be, of course, the sum of these four sides. So P, which is the perimeter, will be equal to x plus y plus z plus omega, with x, y, z, and omega part of the set of natural numbers as the condition of the problem states. Now, by the condition of the problem, we also know that x is a divisor of p, y is a divisor of p, z is a divisor of p, and omega is a divisor of p. This means that there exists x1, y1, z1, and omega1 from the set of natural numbers such that p divided by x is equal to x1, or that p is equal to x times x1, and also p is equal to y times y1, p is equal to z times z1, p is equal to omega times omega1, or that p is equal to the product of these numbers, and these products are equal among themselves. Now, we know that the perimeter of this quadrilateral is equal to the sum of the sides, so p is equal to x plus y plus z plus omega, and we make the substitutions which we deducted up here. X is equal to p divided by x1, y is equal to p divided by y1, z is equal to p divided by z1, and omega is equal to p divided by omega1. So we will get that p is equal to let's say to p divided by x1 plus p divided by y1 plus p divided by z1 and plus p divided by omega1. We let's say we factorize p on the right hand side and we simplify p on both sides of this equation, and we will get a very important result, that 1 divided by x1 plus 1 divided by y1 plus 1 divided by z1 plus 1 divided by omega1 is equal to 1, and we call this the equation number 1. We now suppose, by contradiction, that the four sides of the quadrilateral are different. So x different from y, from z, and from omega. This would bring, of course, that x1 is different from y1, different from z1, different from omega1. Now, without loss of generality, let's accept, because this equation over here is symmetrical, let's say in the meaning of x1, y1, z1, and omega1, let's accept that among 1 divided by x1, 1 divided by y1, 1 divided by z1, and 1 divided by omega1, the maximal of these four values is 1 divided by omega1. So we would have that the sum of the equation number 1, which is equal to 1, is smaller to 4 divided by omega1, because this is smaller than 1 divided by omega1, this expression smaller by from 1 divided by omega1, and the same we can say over here. So from this inequality we get that omega1 is smaller than 4. We will call this the inequality number 2. Now we know that in the given quadrilateral, of course, x plus y plus z is greater than omega, because let's say x plus y plus z, as we see over here, is greater than omega, because both these sums represent the distances from point A to point B, In the first example, we have done the path omega, while in the second example, we have done the path x plus y plus z, which of course is greater than omega. So, in this expression over here, we would have that by substituting x, y, z, and omega, we would have that p divided by x1 plus p divided by y1 plus p divided by z1 is greater than p divided by omega 1. We factorize and simplify p to have that 1 divided by x1 plus 1 divided by y1 plus 1 divided by z1 is greater than 1 divided by omega 1. But this expression over here from the equation number 1 is equal to 1 minus 1 divided by omega 1 over here. So we will have that this is equal to 1 minus 1 divided by omega 1, which is greater than 1 divided by omega 1. Or that 2 divided by omega 1 is smaller than 1, or that omega 1 is greater than 2. So we got another inequality, which we call inequality number 3. Now, from the inequalities number 2, that omega 1 is smaller than 4, and inequality number 3, that omega 1 is greater than 2, we get that omega 1 is equal to 3, because this is the only possible value which fulfills these two inequalities. But given that we have taken that the maximal value of 1 divided by x1, 1 divided by y1, etc. is 1 divided by omega 1, we say that 1 divided by omega 1 is 1/3, or 1 divided by 3. This means, given that the other values are smaller but different than 1 from omega 1, we can have that, let's say, the maximum of 1 divided by y1 can be 1 divided by 4, the maximal value of 1 divided by z1 can be 1 divided by 5, and the maximal value of 1 divided by, this would be x, I'm sorry, is equal to 1 divided by 6. So, because this happens because omega 1 divided by omega 1 is a greater value, and the other values cannot be equal to each other. So, by this deduction over here, we will have that the sum of the inverse of x1, y1, z1, and omega 1 is smaller or equal to 1/3, which is 1 divided by omega 1, plus 1/4, which is 1 divided by y1, plus 1/5, which is 1 divided by z1, plus 1/6, which is 1 divided by x1. But the sum of these four fractions is equal to 57 divided by 60, which is smaller than 1. This inequality number 4 is very important because this inequality breaches the inequality and has a contradiction with the equality number 1, with the equation number 1 that we have up here. So this means that given that we have a contradiction over here, the initial supposition that all four sides are natural numbers and different from each other is not correct and is false. So this means that our proof is concluded and that at least two of the sides of this quadrilateral are equal to each other. So, to make a little bit of recapitulation of the situation that we discussed up here. So, as we said, we initially supposed that the four sides of the quadrilateral were different from each other. This brought that even the divisors, let's say, the result of the division between the perimeter and each of the sides, which were x1, y1, z1, and omega 1, are different from each other. We suppose that let's say the maximal value between these four fractions was 1 divided by omega 1, and we concluded by two inequalities that the only possible value of omega 1 was 3. So the maximal here was 1/3, and we deducted, of course, then the other expressions, which are different from each other and smaller than 1 divided by omega 1, could at maximum be 1/4, 1/5, and 1/6. But if we make the sum of these four possible maximal values of the fractions, we still reach to 57 divided by 60, which is smaller than 1. And this does not fulfill the initial condition that we had from the conditions of this problem. So, hence, having a contradiction to the supposition that all four sides are different. Please, if you like this problem, don't forget to like, comment, and subscribe to our channel up to our next uploads. Thank you for your time, and bye.